Oh, welcome to our Bringing the Heat webinar series. We are re-recording this webinar due to a technical issue associated with saving the live version. But my colleagues Bob Glass and Gorm Heron are here to review this important webinar with this group. So, that being said, we had many people who tuned in to our original webinar. Lots of questions were asked along the way. So I'm here to help guide questions as Gorm, our Chief Technology Officer, talks with Bob Glass, who managed this important high temperature project. So with that, Gorm, would you give us an introduction about this project?
I can certainly do that. By the way, the star you see in the background there is the location of the Joint Base Elmendorf-Richardson site, also called JBER. That's where the project took place. What we have been looking for is a solution for PFAS impacted soils, and this is our third field project. You can see at the top there with the orange liner on it, that was a project of so we're treating an existing stockpile. 1 out of 51 stockpiles they had at Eielson Air Force Base was treated with thermal conduction heating. Each of those pipes sticking down is thermal conduction heater boring, and there's a heater element inside. We'll show you what it looks like in a moment. On the right upper photograph, that's Beale Air Force Base in California. It's an in situ field demonstration. So we treated PFAS impacted soil from a fire training area from surface down to 13 feet below grade, which is where the high concentration impacts were. And then the third picture at the bottom there is the actual case study, the JBER above ground treatment, where we treated 2,000 cubic yards of PFAS impacted soil waste. As you can see, we used thermal conduction heating. The first two, they were vertical or slanted a little bit, heaters. In the third one, they actually lay horizontally through the pile. And Bob will explain to you later on how we did that and how it worked. Just a few things to take home from this presentation. 355 kilowatt hours per cubic yard. That was the energy we used to heat the soil at JBER. So the demonstration you see there, it's to a lot of people a surprisingly low amount of energy. The soils were reasonably dry. We kept them dry. You see them under a tent there, but that's not a crazy amount of energy, right? And that was one of the objectives of the demonstration, is that when it's not really small, when the surface area to volume ratio is not super high, you can get really decent energy usage, which really isn't that much. You cannot haul the soil very far in a truck before you've spent more energy on the diesel that truck uses. And the other thing, take a home message, is we took 30 soil samples of the soil at JBER at the end, and you will see how low we can go with the treatment.
We do have a question, Gorm, about the in situ project that came in from the audience. So their question was specific to the smear zone and the shallow saturated zone. How effective is this treatment in that area of the ground surface? Can you talk through how high above the water table we need to be?
Yes, because any groundwater that can replenish itself would quench the temperature where the groundwater is to the boiling point of water, so 100 near the surface of the water table. Because of that, our in situ solutions are effective above the groundwater table, and in low permeability, soils like clays that have a high capillary rise, we may have to be 5-6 feet above the water table to be able to dry them out and get them to our target temperatures. In more permeable aquifers where there's not a whole lot of capillary rise, you might be able to get a little closer to the water table and still dry out without water wicking back up. So somewhere between 3 and 8 feet above the water table is typically where where the in situ treatment can be effective from there on up to the surface. In this case, at Beale, the water table is a whole lot lower, so it was not really a concern. What we were challenged by there was perched water that was coming in from the side, but that's a story for another day.
So Beale, Eielson, J-Bear, we all, those three projects included massive team of contributors. I know that you were going to acknowledge some of them in the next slide. Thank you.
And we're so grateful to these firms. ESTCP has essentially funded all three of these projects, and Defense Innovation Unit selected us to do this demonstration. And there's some amazing people in each of these organizations that we're thankful to.
Okay, so switching gears a little bit, let's talk with Bob about how exactly you were able to handle the thermal desorption of 2,000 cubic yards of soil and debris at the J-Bear sites. You want to dive into some of those details?
Sure. I think the first thing we can do is just talk a little bit about what TCH is, for those who might not be familiar. The way I like to explain it, that I think it's easiest to understand, is to think of your toaster at home. The way that works is you pass current through a resistive element. It gets red hot and radiates heat into your bagel or whatever you're cooking. And effectively, that's what we're doing here on a much larger scale. We have resistance wires that we pass a current through. It gets very hot, and that heat radiates into the soil, which we're trying to treat. And you'll see in an upcoming slide exactly how we install these heaters into the soil pile to be able to deliver that heat.
Yeah.
Go to the next one.
Yeah, maybe I'll just add real quick. You see it glowing there. Before we took these horizontal heaters to the field, we tested them at our facility in Indianapolis, and that's actually a photo of it lying horizontally in one of our test beds that we built for this.
It's a good point, and they get very hot, upwards of 1,000 degrees Celsius for the actual heater element, and then it radiates out. So,
yeah.
It's a little stronger than a toaster, I guess.
Not your average toaster.
Not your average toaster. So yeah, working in Anchorage, Alaska, lots of fun. So one of the first things that we had to do was devise a way to keep our soils dry through the winter. So the first thing we did was build this structure that you see here. It was enough to contain our 2,000 cubic yards. The pile that you see in the picture on the right is actually the feed pile that we pulled 2,000 cubic yards out of. That is a 6,000 cubic yard pile, and that dirt was divided up amongst 3 vendors for this demonstration. So the first step was to build this structure you see here, and then we move our soil in, and the next slide will show you how we did that.
Mm-hmm. All
right, so yeah, we put down a liner on top of our base layer, which also has heaters in it to provide insulation. It's hard to find a good insulation that can withstand 2,000 cubic yards of soil on top of it. So we just play to our strengths and use our technology to create a heat front below the pile. And then we essentially built it like, I think you referred to it as a lasagna, Gorm, which I like better than my cake analogy. So we would put down a little bit of soil and then bring in our infrastructure, put in more soil, bring in some pipes and heaters and all the things that make up this pile. And I think the next picture shows that a little more clearly. Yeah, here you go. So we fabricated, what you're looking at here, these pipes are actually the heater casings themselves. It's what that resistive element sits inside of. We fabricated all of this on site and then proceeded with building the lasagna, like you see here.
I love lasagna, but this does not look appetizing.
Yeah. Of course, these heater casings are super heavy. So this, Bob, was what you came up with for, dragging them in, right? How long were these heater casings?
Yeah, it ranged. So our longest ones were about 120 feet long, and those were on the bottom. And because it's a trapezoidal shape, they got slightly shorter as they went up. But yeah, I wish I could take credit for this unique way of pulling these up. I cannot. That was the field team. They did an excellent job managing a a difficult project. It was very tight here, not a lot of space to maneuver and to swing around a 120-foot 4-inch pipe, but they did a fantastic job.
Cool.
Someone has submitted a question about temperature monitoring. Can you explain, what a TMP is and how they fit into this soil pile that you constructed?
Absolutely. Gorm, can you go to the next slide? Because I think it shows a little more of the infrastructure coming out of the pile, and I can talk about that.
It does, but if you allow me, I'll just go back one slide first, Bob.
Sure.
Look at that little co-located pipe here, right? Yeah.
Perfect. Yeah. So for temperature monitoring on this pile, we had really two ways to do it. The first was a TMP, or a temperature monitoring point, and that's a casing that's placed in, if you could envision a triad of heaters in the pile. It's placed in the middle of those, and it has multiple sensors in this pipe to measure temperature at a discrete distance into the pile. The other way we measure temperature is what Gorm just showed. It's that small pipe directly next to a heater casing. And we use that to monitor the temperature of the heater itself. And that helps us optimize that power input and ultimately the heating of the bulk soil.
Yes. And we have these sensors that are inside those pipes, right? And we have multiple of them going along the length of the pile and feeding us back temperature data. I believe what I'm circling here is one of the midpoint ones in between heaters, and then you can see a little pipe up here next to a heater, and that's where the co-located TMPs were used kind of for thermostat-like control of the heat.
That's a good way to put it.
While you're on this slide showing the pile, someone did submit a question about vapor extraction. Can you talk a bit about how these contaminant vapors are collected and what your expected radius of influence would be? Yeah, please elaborate on vapor recovery.
Sure. I can talk about how we installed them, and then if Gorm wants to talk about radius of influence or anything like that, that would be fine. So they're installed basically in the same way as our heater casings and our TMP casings. It's a horizontal screen that's embedded into the soil matrix with a sand pack around it. And then it's hooked into a vapor recovery piping network and ultimately routed back to our surface treatment equipment. The pile operated under a low vacuum for the entirety of the heating phase, and we're just constantly pulling out that steam and vapor. I believe on this one we had 5 vapor recovery points, main vapor recovery points. So the radius, of influence, Gorm, you could probably speak better to that.
Yeah, so I'll circle them. Hopefully you can see my screen. Here's one of them coming out. There's another one here, another one over here, and there's 3 more. So I believe we had 6.
We had 6, yes.
And they're 2-inch in diameter, and they have different slotted sections along the length of the pile. It's not one long screen. It's screen, pipe, screen, pipe, screen, pipe, so that we get basically suction selectively at areas, just so we can pull that way. We can also use these as inlets if we feel like we need to have air sweep across, from one end, from the center of a pile towards the outer edges. We can have some of them be open to atmosphere and the other ones pulling vacuum. The main idea is we need to have enough open area in these screens so that all the steam can get out. When we're heating quickly at the beginning of the project, drying out the soil, we make all the water that's in there turns into steam and comes out as a gas through these 6 extraction wells. And they have to be big enough, have enough screen area for that. Later on, the flow goes way down, and we have now non-condensable air coming out. Some of it's CO2 from some degradation of natural organic matter and so on. But there's much less flow, and we now have to, if we want more flow, we have to introduce it through either leakage through the pile or controlled through some of the screened sections here. We do not rely on on sweep and radius of influence the way you do with the normal SVE system that you design for the field, because everything gets cooked to temperatures that are 400 degrees Celsius or higher. We've shown in the laboratory, even in boxes, with or without sweep of air across them, we still get good results without the direct airflow through. Just there's enough gas evolution and flow out of these soils at the high temperatures, and we get treatment, even if there's a stagnant point. You know, you have this. You can imagine you have the same vacuum between these two, so there'll always be like a stagnant zone in between. It doesn't seem to be an issue. We sample the soil right in the middle, and we get excellent results. So the traditional radius of influence stuff doesn't really apply to this type of thermal.
Well, let's talk about the insulating layer, Bob. What did you end up using at JBear at this pile?
Yeah, we ended up using a mineral wool product. It was actually very hard to find an insulation that's rated for as high of a temperature as we would be exposing it to. We targeted an R30 on this particular pile. It worked very well, but yes, it was a mineral wool, and that's actually what the picture you're looking at here is capturing, is them installing that. You'll see the red liner that's over top of the soil. That's a high temperature silicone impregnated liner that can withstand that temperature, and then we place the insulation over top of that.
And I'll just show that show what it looked like afterwards. So the rock wool is underneath this additional tarp that you see on top of that, this top liner, just, you know, keeping it a little more vapor control, a little more, moisture is kept out by that. So the rock wool was in between the black liner and then the orange-red one we just saw.
There's a little bit of equipment that is shown in this photograph, electrical and some data communication equipment. But could you also talk about the vapor and liquid treatment equipment that was utilized at JBear?
We can definitely do that. I'm going to have to jump the slides a little bit. Just a quick repetition. Here you see one of the vapor extraction pipes, I believe. Oh, no, that's a TMP. But all the 6 vapor extraction pipes run into a manifold, and they run off to the side to what we call the vapor treatment system. And if I jump down to it, it is essentially, you have to imagine the pile over here. Vapors come to a scrubber, which is water circulates around, we quench the steam, and we have vapor at a lower temperature that goes to another condensing step to remove any more steam and droplets. And then we treat the vapor with vapor phase carbon. So the simplest vapor treatment method is out there, right? We avoid thermal oxidation and any type of combustion of these vapors, because there's uncertainty as to what should be the treatment temperature, the residence time for these thousands of potential compounds. There's no Stockholm Convention guidance for that yet. However, cool it off, make it ambient temperature, run it through best available technology, carbon adsorption. We know it works, and we've documented that it does by sampling using the OTM 45 and 50 vapor sampling methods. So we know we're capturing mass in the carbon. We know our emissions are very low and acceptable. Same thing on the water side. Everything gets cooled off. And the water, the condensate, goes through liquid phase granular activated charcoal. Samples before and after. We meet discharge criteria, and we sometimes hold the condensate, the treated water, until we have the analysis back, and then we can get rid of the clean water. So that's TRS's approach to handling PFAS impacted vapor, is essentially cool it off and use very simple technology to treat it.
And Gorm, I think it's worth noting that as regulation and guidance becomes more clear, we do have other options for treating vapor. We do own oxidizers, and we use them frequently on other projects dealing with other contaminants, and they could certainly be implemented here if it goes that way. But for now, using the carbon is the easiest, most cost-effective solution for us.
Yeah. So, and it's very, it's a good thing you say. One of the things, metrics we also had in our performance assessment was some sustainability criteria in some of these PFAS projects, and we actually looked at it. I looked at it at one time. So we used 355 kilowatt hours per cubic yard here for the whole process of heating it, and very little energy for this system. If we had used thermal oxidation and we had gone to the temperatures we believe are needed, which is 2 seconds at 1100 Celsius, is kind of where your default. If you don't know if you can go lower, we would have used more energy destroying the vapors than to heat the soil. More energy, but a significantly higher amount just to process the vapor stream. So while thermal oxidation is possible and is used for a lot of contaminants, it really uses a lot of gas and energy, and it's fossil fuels. It's not something you can easily make sustainable either. Because the main commercial thermal oxidizers are run on natural gas or propane.
So I know that I forced you to skip ahead a little bit to talk through the kind of process flow diagram, but we do have some slides dedicated to the performance of the system, right?
Yeah. And I can talk to those. So it's a thermal solution. We've learned from the lab studies and the first 2 field projects, 400 degrees Celsius, we get excellent results. We get really strong soil reductions in concentration. So we'd like to go to at least 350 if the requirements aren't all that stringent, 400 if we have very low soil pulls like we did here, and a little higher if we want to be certain. And what you see here is the temperature evolution. We have a little less than 3 months on the time scale down here, and we actually beat our numerical heat model by a couple of weeks. We were expecting for it to take a little over 100 days, and we were done in 96 days, I think it was. And the typical kind of profile is heat up real quick to the boiling point of water, sit at 100 degrees until all the water has been removed, and then the temperature rises much quicker in the dry soil as there's less heat capacity and the steam has been removed, and you basically have this beautiful temperature rise. We ended up somewhere around 600 degrees C on average. And you might ask, why did you go that long? Why didn't you stop when it crossed 400? That's because these are our averages of different sensors, and there were 5 sensors in each of them. So we were reaching 400 degrees at the edges, where it's a little bit cooler, around this period of time when the averages was a lot higher than 400. So that's why we want to make sure we had good treatment everywhere, including in the coldest locations, because that's typically where you find a little mass lift if you have any at the end. Then again, just the metrics: 710,000 kilowatt hours used for the heating, 2,000 cubic yards, and that equates to about 355. So, and the reason we could get this low energy usage is because of the insulation below and around the soil, making it quite energy efficient.
Nice when you can take the time to build it out with efficiency in mind, right? But not always the case in situ. This is an exception, I think, with these ex situ applications.
Yeah, and the larger the demonstration is, or the treatment is, the better the numbers, right? So this was 2,000 cubic yards. We can go lower than this if we were building a bigger pile with lower surface area to volume ratio. But for the moment, we're just sticking to what we can prove, which was this number, which was pretty favorable. Yeah. So that's like $50 worth of electricity in most places with normal electricity rates per cubic yard, and it cost a lot more to do other things to the soil.
So speaking of soil, Bob, let's talk about how you collected the soil results in the end of this project, at the end of heating, and what those results ended up showing.
Sure. It's linked to the temperature slide we were just looking at, because we located each of those temperature sensors directly adjacent to one of our soil sampling points, and we had 30 of them. And we did that so that we could correlate temperature to concentration. We did 2 rounds of soil sampling, one at the beginning of the project to establish our baseline, and then one at the end to confirm treatment. They are represented here by these blue dots. It was a little tricky with the pile. How do we access the middle of it, especially at the temperatures that we were seeing? I mean, it was over 700 degrees in a couple locations, so extremely, extremely hot. What we elected to do was install sample ports, and you can see one of them here. And we actually went in with a hand auger, which all of our consultants on the call are very familiar with, and retrieved results that way. But you can see, looking down that pipe, it was extremely, extremely hot. So it was not your average soil sampling event. There was lots of things we needed to do to cool the sample prior to bottling it and everything else. But yeah, we did it by hand, believe it or not.
What company did we use for sample analyses, soil sample analyses, and what was the turnaround time? There, we did receive a question about that.
Yeah, we ended up using Eurofins, who everyone is familiar with, and the turnaround time was actually quite reasonable. We were able to get it down to approximately 10 days. So pretty good turnaround time for soil.
Yeah, awesome. Well, before you get into results, do you want to share with folks what the starting concentrations were? I know we've kind of seen a spectrum of them from the different projects that we've worked on, but
yeah, I can take that one.
Sure.
Might be relevant. Whoever posted the question may be interested more in general than just JBER. Our starting soil concentrations was around 20 to 30 micrograms per kilogram at JBER, and that was PFAS dominated. There was other compounds as well, but mostly PFAS. So in comparison, we had at Eielson, which you see here, we had 272 micrograms per kilogram, so an order of magnitude higher starting concentrations, and another order of magnitude higher at Beal, the in situ project, we had 2,000 micrograms per kilogram in this topsoil from this fire training area. So the interesting thing is the starting concentration doesn't really matter that much for our process, because in order to get PFAS reduction from, say, 30 micrograms per kilogram down to a target, most soils have backgrounds in the 1 to 3 micrograms per kilogram range. Believe it or not, if you go to even the forest of New Hampshire and take topsoil samples, you're in the 0.5 to 1 to 2 microgram per kilogram range background from basically rain deposition. But our goal was also to meet the EPA RSLs at this site, and they are in the 0.0 something, 0.1 microgram per kilogram range. So we essentially wanted to reduce it from, say, 30 to 0.1 or less in order to basically remove all doubt about what we can do and how low we can go with the treatment. It may be that for scale-up applications for other sites, we'll have targets that are a little bit higher than that, like the Alaska regs say 3.0 for PFAS, 1.7 for PFOA. However, we've treated the soil to much, much lower concentrations here. Excellent. Sorry, that was a long-winded answer to what was in concentrations. I could just have said 30 at JBER, but it's a good story. I think when we had 2,000 at Beal, we were still able to reduce those concentrations to meaningful low concentrations at the end.
Yeah. So Bob, let's talk about the results that we ended up receiving from. Yeah, there you go.
Yeah.
Want to walk us through this?
Yeah. I'm proud to report that all 30 soil samples were near or below detection limits. We used the EPA method 1633, and then we did a composite sample of all of the samples, and that was below detection limits. And the detections we had were for lesser known PFAS. It was not for the main contaminants. And I believe we have a table showing all of our results. Yes, there you are.
Mm-hmm. And what you have here is essentially the, I know it's a big table, but maybe we see the different PFAS compounds, some of them here, and we start looking at the detection limits, micrograms per kilogram. You can see the detection limits were pretty low. We talked about starting concentrations of 30 on this scale and 2,000 at Beale. So in order to get non-detect, we have to be below these extremely low concentrations. And we got the EPA RSL in here. Some of them are much higher, some of them are lower. And then we have essentially the highest we found in any of our 30 post treatment samples is here. And you, like Bob said, non-detect. We had tentatively identified, some Adona, which is an interesting one, and this PFX HXA compound. J, I think, means it's less than the reporting limit, but greater, and it says that in the bottom, greater or equal to the MDL. So we also went back and sampled those highest concentration soil like a month later, right, Bob? You went back to those two locations that had just a hint of something. And then we were non-detect for them. So treatment continues after we turn the heat on. It keeps curing itself, if you will. It's like a Christmas roast. You take it out of the oven like 30 minutes before you serve it, and it keeps cooking a little bit, right, from the. And the same thing happened here. We were very near detection limits, and when we turned off the heat, and then we came back a month later, took samples again, we were below detection limits.
All right, we got roasts, lasagnas.
I was just thinking that.
Toasters.
A lot of food references.
I'm getting hungry. No, someone did submit a question wanting to know about total extractable organic fluorine and if we did any before and after heating tests. I think the answer to that question is yes, we did run those tests, and we are awaiting the results.
That's great.
Yes, and we've seen several other companies attempt to do fluorine mass balance and to extract total fluorine. Of course, there's so much background fluorine that is not PFAS related, so you typically, that is like having 1,000 or something and looking for a change in the 1 to 10 that's actually PFAS related. So total fluorine typically is not very meaningful. Total extractable fluorine is not that relevant either. There's a lot of background. Then there's ETOF, extractable organic fluorine. I've seen a couple of studies of that, and it's maybe more 10% of the total fluorine. So there's more of a change in that and a reduction in that. But there's just so much other fluorine that these relatively crude extraction methods, they measure so much more than the PFAS compounds that could impact us, that it's hard to show very good reductions in them because there's inorganic fluorine that doesn't ever vaporize, for instance.
Yeah, all good points.
Like if there's any toothpaste residue in a sample, right, you'll have super high fluorine but no PFAS.
We did receive a question about a mass balance and how is that calculating out right now. I know that we are also waiting for additional air emissions data before we can perform the mass balance, but performing a mass balance assessment is a part of this project scope of work. Is that correct, Bob and SCORM?
It is, yeah, and we are still waiting on data back for that.
Yeah.
Okay.
And we have done it for other projects before. It's very. You can easily do a mass balance, but you cannot typically close the mass balance in the field for a number of reasons. Imagine this being the roast or the pile. There's in situ degradation, like Bob showed us looking down through that TMP pipe. You saw orange glowing soil. So a lot of the mass in the ground actually degrades and never comes out. And then so you have a fraction of the PFAS mass come out in the vapor. You then run it through the scrubber. Most of that goes in the liquid phase and ends up in the first carbon vessel here. Some of it sticks to the sides of the holding tank and the pipes and has to be rinsed at the end. But a small fraction goes to the carbon on the vapor phase. Typically less than 5 or 10% ends up here, and somewhere less than 50% ends up here. And then we got something stuck to the surfaces, and then we have the in situ destruction, which is very difficult to quantify, but we know that some of it does destroy there. Kurt Pinnell from Brown University did a mini version of this in the laboratory with glassware and tubing that he could rinse, and he was able to close the mass balance pretty good. He basically knew how many micrograms or nanograms of PFAS he started with, and he got some of it in carbon, the two different phases, and then most of his mass he got when he rinsed the equipment at the end in methanol and analyzed that methanol. So it also depends on how long you run. If you run a short test, you get a lot on the surfaces. If you run a really long test, it kind of runs through, and the quantities in the carbon and so on become more larger fraction. So PFAS is just tricky, especially when it comes to sampling and analysis, and the fact that it's so surface active makes it hard. Even a water sample, how do you cut it in half in a good way when most of the PFAS is sticking to the surface of the water sample, not in solution, for instance. So even making a dilution is difficult.
Yeah, all good points. We did receive multiple questions about costs. So I will ask, what's the average cost per cubic yard to treat soil using this method, these temperatures, with PFAS desorption in mind?
Yeah, should I take that one, Bob?
Sure.
So this is the largest demonstration we have done for the 2,000 cubic yards, and I explained how the electricity for the heating is somewhere in the $50 per cubic yard range. In Alaska, it's a little more because we're not paying, say, 15 cents per kilowatt hour. We probably pay more than that. In other states, it's less. So the energy, say anywhere from $40 to $100 per cubic yard, and then the rest is totally dependent on where it is.
So many different factors, right? So many different ones, yeah.
But I think it's safe to say we will struggle to be under $500 per cubic yard all in, just because of the sizes of these batches typically, and all the manpower. And you saw how Bob built the system, right, with the heaters, the silicone impregnated fiberglass liner, the rock wool that can be recirculated from site to site, recycled. The tent we used to keep water out so that we could finish it within one Alaska field season, so we didn't get frozen over essentially at the end. All of those were Alaska specific things that made it more expensive there. If we were in a dry area, didn't need a tent, we could remove that requirement and that cost. And if there's a lot of soil to treat, like another project we're doing now in Puerto Rico, we're building a structure like this and we're reusing it many times over. And of course, those costs are like less than half of what these costs were, because we're reusing and recycling heaters, casings, the insulation gets peeled off and then comes back when there's a new batch of soil. So yeah, long-winded story, but the more soil you have, the lower your treatment cost is going to be. And there'll be an asymptote somewhere that's in the $500 to $800 a cubic yard range for us, I believe, just because of all the work that goes into it.
Yeah, we'd be happy to take a look at the project, right? The scale of the project, site features, the scope of work, water content of the soil. We'd be happy to, learn a little bit more about others' projects to try to develop some site-specific pricing for for consideration. But also, I mean, Bob, as part of this project that you're completing right now with your team, you guys are going through a pricing analysis, and you're tasked with pricing various different scenarios, right? That all need to be published. So I think the short of it is more to come from TRS on this subject.
Yeah.
Yeah. And that'll include scale up modeling for larger sites and large volumes of soils.
Yeah, definitely. So, I have a ton of questions that the audience have submitted still. I don't know if there's any specific SCORM, Bob, that you want to share with the audience, but I'll start firing off all these remaining questions if you want to put up with it. But there is one about the physical properties of the soil and how they change when you achieve temperatures like this. Can you talk about how we could maintain soil physical properties, or if there's something that could be done at the end that would make it organic rich again?
Go ahead, Gorm.
Yeah. So the process lowers the fraction of organic carbon significantly when we treat over 400 degrees C here, right? Like most soils are basically 99% quartz grains or clay minerals or other basically other minerals that do not get affected by the heat, other than they get warm and they can maybe glow a little bit, but the fraction of organic matter in most soils like less than 1%. So that can burn off and come out of the pile along with the PFAS vapors and so on, and the steam that comes out. If you want to reuse that soil at the end, you have to mix it with something and not maybe mix it with soil that hasn't been heated or some sod or so on. It's ideal to be used for fill stuff, right? It won't grow weeds very easily for a long time afterwards. You probably want to water it because it's bone dry. So when you move the treated soil out of the pile, you don't want a whole lot of dust. So you can spray water on it for dust control purposes, make it moist again, and then reuse it.
And that's exactly what we had to do here when we moved it. This specific soil, and this may be just specific to Alaska, but it was very sandy, gravelly. It was drier than I was expecting. So that was this, specific soil makeup, and post heating, it didn't change all that much. I was surprised. I think in a more clayey soil that might be different, but here it still looked pretty similar, although it was a little bit dustier. So we did rehydrate it as we were moving it out of this place and taking it to its disposal location.
You mentioned the nature of the soil, Bob, and one thing that a lot of people don't know is that we can have boulders in here, we can have concrete debris, we can have asphalt with PFAS in it mixed in with the soil, and we don't have to sort it. We don't have to basically process the dirt and remove the boulders and all that first. We just put everything in the pile and cook it at the same time, right?
I'm glad you mentioned that, because we had all of that actually in this pile. This came from an excavation on a military base, and there's lots of interesting things in there. But specifically the cobbles, I mean, there were just some big, greater than 1 foot cobbles, and they just go right in with all the rest. And the concrete, asphalt, it can all go in there and be treated.
So there's other options for treating PFAS impacted soil, right? But it's important to note that we didn't have any other fractions. There's not another pile here that had to be taken off site because we couldn't treat it. It's all in here. There's no fine fraction that goes off site, and there's no coarse fraction that goes off site for disposal. It's all in here.
Someone did ask a question, why would you adopt this ex situ method over in situ. So in this case, at J-Baird, the soil was already stockpiled, right? So it's not in situ. In situ is not an option. But someone asked the question separately, if the soil was in situ, why would you even bother doing it ex situ? I guess, do you want to talk about maybe just energy demands and how much lower they are when you're dealing with the pile?
We've basically grown into TRS group by treating DNAPL sites, PCE, TCE, and most of them are pretty deep. It keeps going deeper. It goes to the water table, keeps going down because it's heavier than water. So a lot of our sites are 30, 60, 100 feet deep. However, with PFAS, because of its properties, in fire training areas and other locations, it really doesn't typically go that deep. You have, like, also with PCB contamination, dioxin and furan contamination, most of your mass is in the top 5-10 feet. So that gives it a relatively poor geometry for in situ, in that you have such a large surface area and such a huge bottom area, that your heat loss is very substantial. Like at the first project I showed you, the Eielson one, where we treated an existing pile. It could also have been in situ, just of a little mound impacted by PFAS. We use twice as much energy per cubic yard because of the heat loss to the surroundings. So we just do the math, right, and we figure out what does it cost to scrape this into a pile, excavate it. It's not deep excavation the way you think of it with shoring and all that, because it's relatively shallow soils, and the cost to bulldoze it into a pile like this is relatively low based on or compared to the energy savings.
Yeah, excellent point. In situ, you might eliminate that soil management, costs and hassle associated with managing the soil if you just do it in situ, but you're using quite a bit more energy and the soil's exposed to that much more heat losses.
Yeah.
All right, let's touch on demobilization of the system. Do we have the ability to reuse any of these components that we're looking at right now, Bob?
Sure. Yeah, we can reuse the majority of our components. All of the electrical infrastructure that you see here, all of that is TRS owned and reused. All of the cabling, the stainless steel piping after it's deconned, we can reuse all of that. We typically reuse the temperature sensors, and it's actually easier to talk about what we don't reuse. And what we don't reuse is generally going to be the heater, that resistance wire that we looked at earlier. We're generally not going to reuse that, although we could. It's fairly cheap, and we custom build them for each individual site, so we're generally not going to reuse that. The casing that heater sits in is exposed to extremely high temperatures. We're generally not going to reuse that. It does get a little beat up when it's getting exposed to 1,000 degrees Celsius for months on end. So we probably won't use that, and likely the screens and things that are in the pile here, we're not going to reuse that. So most of the casings, one-time use. The liners will be one-time use, but pretty much everything else we're going to be able to either recycle or reuse, including the building over top. And
And I may add, at projects where we don't run the heaters as hard as we did here, we do reuse the heaters more frequently. We have a site in Washington State where we just finished the first half of the project, and the heaters have been moved over to the second half, and the same basically thermal conduction heater elements are being used for phase 2 at a landfill site there.
Over and over and over again.
Yeah.
Love it. All right, last question of the almost hour, I guess you could say, is last question that was asked. When do you anticipate this technology is going to be available for full-scale implementation? So Bob Gorm, I don't know if you want to make some comments about the success memo, as it is called under this DIU program, but I think now would be the time.
Yeah, and essentially the short answer is now. I mean, it's commercially available. We've done this demonstration. We did the other two PFAS projects. The equipment is the same as what we're using at sites now. Even did a project in Europe as well with the same technology, not for PFAS, but it's available. It's just how close you put them together that determines the temperature you reach in between, and that is driven by your contaminants. And in the case of PFAS, we use this proven technology. We just put the heaters closer together and get to higher temperatures. So it's available now. If we had been using thermal oxidation, we would have hesitated a little bit, maybe for guidance as to residence time and target temperature in the oxidizer, but we don't have to because we went the opposite way. And the great thing about this ESTCP and DIU project is that it's so heavily reviewed and scrutinized by independents. And at the end of it, they are preparing essentially a memo of our basically how did we do what we said we would do in the work plan, right? And I believe they're in the process of writing that, and gives kind of a government stamp of approval on these guys know what they're doing and say what they are going to be doing. And that gives us a possibility of being contracted a little bit easier with less hurdles to do this full scale. And we're of course hoping that that's going to happen as soon as possible.
With the memo in hand, it essentially allows any federal agency to access this technology a bit more directly outside of the FAR even.
Yeah.
To make it more accessible to whatever agency needs it. So we're learning a bit more about that process and have had some incredible mentors helping support us. But we are getting ready to have in hand that success memo.
Yeah.
Well, I appreciate you both once again for joining us at the Bringing the Heat webinar series, talking about this amazing project. But with that, I think we'll conclude the webinar today. Thank you so much.
Thank you.